Let's talk about fuses because there's quite a wide range of fuses, quite a wide range of ratings. And apart from being the most universally abused component, it's also one of the most important for safety. And in this case, just for entertainment value, I've got some really big fuses and I've smashed one of these open, one that's been pre-blown, so I'll show you that later. A range of standard fuses that you're likely to see. A clone fuse from China was supplied with a product, well, they're all probably from China. Well, no, these ones are made in Britain, actually. And electronic fuses, automotive fuses, and the really interesting one here, which is a high voltage fuse designed to break 15,000 volts in a particularly interesting manner. But before I start this video, I'm just going to completely ruin it by making a really bad 1980s rave reference by getting a big fuse and a little fuse, and anybody who knows the 1980s era will know exactly where this is going. Big fuse, little fuse, big fuse, little fuse, big fuse, little fuse, cardboard box. Oh dear, I appear to have dropped an E. See, I told you it was going to be really tacky, but not to worry. Let's continue. So the first characteristic that confused a lot of people with fuses is the voltage rating. You see, when you have something like a 12 volt power supply and you get a new fuse for it, you read the ratings of the fuse and it's got the current rating, but it's also got a voltage rating. In this case, this fuse is rated about 250 volts. You think, well, can it be used with 12 volts then? And the answer is that yes, because the voltage rating is the maximum voltage it's designed to break. The current rating is what's really important here. So you've got the voltage rating will extend, say for instance these ones it's 250 volts, but it gets a bit more complicated than that. For a typical 1.25" or 32mm fuse, it goes up to about 500 volts for many of the styles. For the industrial fuses, it's rated for, well, in this case, it's rated 415 volts. And then, of course, at the top of the range, we've got 15 kilovolt, this 15 kilovolt fuse here, or higher. The trip characteristic is the next thing that confuses people. You see, you get different ratings of characteristics for tripping. And if you use the wrong fuse, it might be the correct current rating, but it will just keep blowing all the time. It will seem as though there's another fault, a recurring fault, when there may not actually be one. You see, you get two standard characteristics. You get the quick blow and slow blow. The quick blow is usually called F, think fast, and the slow blow is called T, think time delay. You know, it would have been nice if they just used, you know, if they used names that actually match the letter on them, but this is what happens. And when you have, say, for instance, a fuse in line with a transformer or some other load that's going to start with an inductive surge, you have to use a time delay fuse, because unlike the quick blow fuse, the F fuse, which is designed to blow quickly, the time delay fuse allows, it's sometimes got a little blob in the middle of the wire, or it might have a little sort of, it might be wound as a spring. And the idea is that instead of blowing instantly when it detects an overcurrent condition, it actually has a slower characteristic. It takes a wee while to warm that blob up and trip. So if you've got a circuit feeder transformer, or motor, the usual type of fuse is a time delay fuse. F fuses are most likely used for loads like just tungsten lamps or loads that aren't going to have that huge inrush. Basics electronic circuitry would usually have just like a quick blow fuse, mainly to protect the components as well. And this is where there's another fuse called FF. Now, FF is a really fast blow, and it's often called a semiconductor fuse. And the idea is that theoretically, it doesn't always happen, the fuse blows so quickly under fault conditions, and it makes it very sensitive to false blowing, but it blows so quickly that it will save the semiconductor device that's connected, like a triac, bridge rectifier, MOSFETs. But in reality, from my experience, it doesn't always save the component, and sometimes the fuses themselves are so hard to get and so expensive that maybe better just use an ordinary fuse and make sure the component's easy to change. Other styles of fuses. Now, what should I cover here? Breaking capacity. That is one of the most important things. You see, quite often you'll see glass fuses that have gone black inside. They've really splattered, and sometimes they'll actually fail explosively. And the reason for this is that the fuse has to be able to break the fault current. And these little glass fuses are only rated to break about 35 amps. And if you think, if this is connected to the mains, if this is connected to, say, something like a industrial unit with a transformer, and something does, a bit of hardware gets loose and something shorts out, then the current is going to be much, much higher than 35 amps. And in that instance, what can happen is this. The fuse blows, and this is a fuse out of a lighting controller I was brought some time ago. It was worth taking a picture of. There was so much damage in that controller. It was a fairground lighting controller, and the ordinary glass fuses have been used. Now, I can understand why people use glass fuses, because you can actually see through them. You can see if the fuse wire is intact. You can't always see if the fuse wire is intact, but in most instances it gives you an easy visual reference as to the state of the fuse. But if you use ordinary glass fuses in industrial application, if you use them in the mains, then because of the high fault current, if there's a dead short circuit and the fuse just blows instantly, what can happen is it can initiate an arc inside the glass tube. Because the filament has splattered, it basically creates a mist of conductive metal, and that it allows the current path to continue as a discharge through the tube, which causes it to be coated. And you can see the inside of this tube is also just splattered with copper. In some instances, if metal plates inside the tube, the actual tube itself can conduct. And what's happened here is because the amount of power dissipated in that arc has been so high, it shattered the fuse. It's really exploded it, and then the arc continued out. The arc actually blew out from there and made electrical contact with other fuse holders, which then more current flowed to those, and it basically went along the whole row of fuses in this. I had to change every single fuse holder in this, partly because the fuses were welded in, and partly because they were so burnt and damaged, and there was also quite a lot of electronic damage in that unit. The person who brought this in had been working on the line controller. It had blown some fuses. He'd gone and put the new glass fuses in. He'd been using his phone as a torch, and then he went over to turn the power back on in this really confined area inside one of the pillars of a ride. And he said that it was just like the loudest electrical bang he's heard. It was just, his eyes were just, all he could see was just a visual dot for so long that he just had to stay put inside that pillar until his eyesight returned before he could actually get back out again. He said it was a terrifying experience. So the reason for the ceramic fuses is that these aren't just a ceramic tube. They're actually filled with sand inside. Now I can bring in a big fuse here that has blown and show you what's inside them. So this is a 160 amp fuse that has blown with considerable force, but the construction is quite interesting. The end caps have 3 little tags on them, and in this case there were just 2 of them with the original fuse links, and I wasn't really sure what I was looking at when I opened these, because it looked like sort of flat tubes, but in reality it's been metal ribbons, and because they've been covered by this sand, when the fuse is blown, the molten metal has blown out into the sand, and it's basically quenched the arc. It's cooled it, and it's also absorbed the metal into the surface, and it's created basically a metal-coated tube. But the metal has been so diffused into the ceramic that it's quenched the arc and it's limited the amount of current can flow. So whereas these little fuses here are rated to break 35 amps, they're equivalent with the ceramic and the sand fill. Will we burst this one open? Yes, I think we will. Will we burst it and check if it does have sand inside it? Scrunchy, scrunchy. Yeah, it's got sand inside it. And this little 20mm fuse is actually rated to break 1,500 amps. It depends on the fuse's rating. That might vary, but you know, the difference is this can break 35 amps, one can break 1,500. So in the event of a mains fault circuit, the force of failure, the ability to break the circuit is much faster, and it basically contain that rupture inside quite safely. The term for these is HRC, high rupture capacity, because they can rupture that current, they can break that current. So next thing to cover, that's the failure mode of glass fuses. Oh, right, okay. Some of the fuses coming from China with products that are bypassing the normal electrical regulations, let's put this one out of the way, may look like our standard plug top fuses in the UK, which are high rupture capacity ceramic fuses. But if I open this one up by just trying to pull the end cap off, there's an end cap come off. All they've done here is they've used a ceramic tube, they've bent the wire, they've threaded an ordinary wire through, there's no sand in there at all. They've threaded a wire through, folded it over the end, and then just pressed the cap on. So this isn't HRC. This isn't going to fail in a controlled manner. It will certainly, the fuse wire is thin enough it will blow, but it won't necessarily break the fault current of a mains fault. And as such, this will go back all the way to the distribution board. And that could cause problems in some instances where there isn't much in the way of further protection or the next protection level is quite high. So it's worth noting that some of these clone fuses are fake. And this brings us on to Poundland fuses, which I don't think are clones. I think these should be compliant. So let's take a look inside one. Let's take a look inside both these packets since they're different and see if they contain the sand and are therefore compliant. So let's well, for a start, it's quite hard to open. Crunch, crunch. There's the sand. Yep, they've got the sand in them. So let's check this one out. And see if these are good. It's always worth checking, particularly if you get fuses from a random source. It's worth checking they have the sand inside them so they can do their job properly. So let's crush this one open. Yeah, it's got the sand again. So both those fuses did contain this sand, which is good. Do we want to take a look inside one of these big ones? Yeah, let's take a look inside this one as well. I mean, there's not ultimately a lot inside. It is a wire going through the middle, and it's sand to break that circuit. So yeah, lots of sand. The place is covered in sand now. That's a bit messy. Next thing, let's keep the exciting fuses till afterwards, the electronic fuses, and go on to this beast, which is a high voltage 15 kilovolt expulsion fuse. And the reason it's called an expulsion fuse will become apparent shortly. Now, if you've ever seen videos of linemen switching, putting in the what they call cutouts next to transformers and overhead lines, things like that, occasionally you'll see them throwing the thing in with their big extendable fiberglass insulated pole, and there'll be a massive bang and a sheet of flame will come out the bottom. And that's actually a deliberate thing. That's how these fuses work. You see, these fuses, and let's look at the rating for a start. This one is slow blow 30 amp. It's rated 15 kilovolts. The number on it is 15TD30. 15 for 15 kilovolts. The T means it's got a time delay characteristic. The D means it's a double tail. The other versions of this just have a little button in the top, and other versions again have a little screw-on cap for adapters. And the ones with the button just have a single tail out the bottom. The type of the situations you use these, this one's designed to be wired at both ends. Basically, you put it round a sort of clamp at the top. Once you've threaded it down the sort of main tube of the body of the cutout, and at the bottom you also cap it off. With the ones in the stud on top, you thread it down, you thread this wire through, put it down with the button on top, and then you screw a little cap on, a contact cap. It's kind of simpler than this, but maybe this is just a better option in some situations. So here's how they work. If you're thinking that this is going to be quite a lot of voltage, inside this tube here is quite a malleable, quite a soft alloy, almost like solder. And next to it is a metal strip. I'm going to make a wild guess here because I don't know why they've got this arrangement, but my guess is that because this, the main meltable link here is probably the main component that's going to blow and possibly create a lot of vapor when the fuse blows. And my guess is the metal strip is also, it's part of the fuse, but it's going to carry current, but the main purpose of the metal strip is probably for strength, because if this is a soft alloy and it heated up under load, it could kind of extrude out and gradually get thinner over time. So I'm guessing that this flat strip here is for that extra strength above that. And when one of them blows, the other will be taking the full current, and that's when the circuit will just blow out completely. And when it does, because it's breaking in this case, it will be breaking about 11,000 volts at hopefully a fault current scenario. The amount of energy dissipated inside that tube is so high that it just physically blows the bottom out. This wire will physically blow out the bottom with a loud bang. You'll see the flame come out the bottom, and then this will just be blown clear and it will just dangle. And at that point, it's just broken the circuit completely, because this will still be, the top cap will still be connected to the high voltage. And there's a good chance that the bottom here, the tube inside will probably be coated with conductive coating. But this is in a carrier tube, and which is slightly proud of that. And this wire will then be so clear that the end will just be basically floating in air. That's how it's broken the circuit. Next type of fuse. Oh, voltage ratings. Here is an important thing. This is a vehicle fuse, and it's actually rated about 32 volts max. It's capable, supposedly, of breaking 1,000 amps. I'm not sure I want to put that to the test. But in the case of a car, if that went across the car battery, I suppose ultimately 1,000 amps could easily flow. But because it's got low voltage behind it, I suppose ultimately it's going to have a slight arc welder-ish effect, but the distance the arc can be maintained at that lower voltage is probably quite low, and that therefore it's going to break the circuit in a controlled manner. Despite the fact that these are temptingly sort of like water resilient because they're all sealed and they've got these caps and they've got the wire pre-terminated, the temptation is there to use them in mains voltage applications. But because it's only rated for 32 volts, if you use this in a mains application, there's a risk that it would just burn. It would actually create a conductive coating here, and then the higher voltage would track across, and you could end up the fuse holder burning and going on fire. So it's not a good idea. You have to use a fuse that is rated for the voltage that it's going to be operated within. So let's talk about one of my favourite fuses for circuit boards, PTC fuses. And a common brand name associated with these is polyswitch fuses. And these are actually a positive temperature coefficient thermistor, PTC thermistor, with a very optimized characteristic. So they've got a very low resistance when a normal current is flowing through them. But as soon as you exceed that current that they're rated at, they have a similar characteristic to a slow blow fuse. They will start heating up, and once they start heating up, then the voltage across them will increase. And it causes an avalanche, it causes a chain reaction that then the resistance increases higher, and then the voltage is higher, it's getting hotter, and it suddenly, if you've got one of these connected in, say, series with a load, and it does get overloaded, you'll suddenly see the load will just suddenly tail off suddenly. And what will happen is that this unit will go high resistance, but it will balance, it will waver up and down. It doesn't just stay at a fixed point, it wavers a bit. And it's basically limiting the current to the load. Current is still flowing through the load, but just enough to keep this hot at the temperature of its tripped state. And you get different sizes for different current ratings, and also you get different voltage ratings, but most of these are aimed at low voltage, sort of 60 volt and below use. But again, you can find a variety of types with the different current thresholds and with the different sort of voltage ratings. And the nice thing about these is you can solder this into a circuit board. If it does trip, if something gets shorted out, all you have to do is turn the power off. And this, after a while, this will have cooled down low enough that it won't, it will go low resistance again. If you turn the power on, the fault's still there, it will instantly trip again. It will go hot again. If the fault's cleared, then this will cool down and it will just be normal operation. And these are also, you get ruggedized versions of these used for deliberate control of loads, whereby it's designed for a very high number of deliberate cycles. So if you've got this in line with, say, a high power solenoid or motor, then when the load's turned on, the motor will run for a very short length of time as this heats up. It will, or a solenoid will operate briefly at full current, but then this will go high resistance and then drop the current down. And either the solenoid will just drop out, or it will hold if it's got a fairly low holding current. And that just means it's about as simple as you could get for a timing device. So let's see, have I covered everything? Tell you what, let's look at the failure characteristics of fuses, because by looking at glass fuses, you can actually tell how something failed. So if this is a glass fuse, and you look at the wire in the middle, and it's gone like this. It's sagged a wee bit, and it's melted into little balls at the end, but the glass is otherwise clear inside. Then that means that the fault that caused that to happen was not a high current fault. It wasn't a bang type fault. It was maybe just a wrong lamp has been put in, or a wrong load, or something's failing and it's gradually going low resistance. And the current has increased to the point that this has exceeded its current rating, but it's not been a dead short circuit. So the wire parts and it just balls up at the end, a bit like when you heat soldering, it sort of goes rounded at the end. The other scenario is when a fuse blows and the inside is just solid. It's all coppery and black inside. You can't actually see through the glass anymore. In that instance, that was almost certainly a catastrophic failure. That was a dead short circuit. Something went bang, something shorted out, and the fuse wire blew with such force that it's plated inside the glass. Other things to note. If you look at a glass fuse and you say, oh, there's the wire inside, that's okay, it's intact. Don't take that as gospel that that is intact, because what can happen is the wire might be intact, it might be correctly bonded on at that end, but it might have broken just out of sight. It may have just detached from the end there. And it's possible with thermal cycling and just age that fuses do gradually age. A fuse can fail without a fault being there. The thermal expansion contraction could just take its toll and it can fracture. And when that happens, it may happen at the end. So always check the fuses with a meter and don't just rely on taking a look through the glass at the fuse wire inside. Next thing, if you've got a big fuse like this and it blows and you're like, oh, where am I going to get a fuse like that? And you've got the option, you can short it out. No, don't do that. Or you can do what some people do, and even with standard plug top fuses, they wrap tin foil around them. Don't do that. You get equipment brought in for repair and people have wrapped a bit of wire around it and then pushed it back into the fuse holder and they say, oh, it's okay, it was the correct rating of wire. It may be the correct rating of wire, but it wasn't in the correct housing. It wasn't inside the ceramic tube. And that gets really, important with industrial applications. If you just put this fuse in and you wrap a bit of wire around and you say, oh, it's okay, the fuse is rated for, here's roughly the size, it's going to blow first. What's actually going to happen if there is a major fault is that wire is going to just splatter. It's going to vaporize. You're going to get a conductive plasma. That plasma is, because it's electroconductive, it's going to spread out and it's going to carry current. And if that then goes on to earth metalwork in the vicinity, you'll get a high current passage to that, and then the plasma will continue. It will get further, it goes on to the adjacent phases, and then you've got higher voltage, high current flowing through this plasma. In short, just like that, boom, the whole panel will explode. Honestly, just the whole panel, the door might actually get blown off it in an industrial application. And I can recall going to a factory, an engineering works, where they'd had a simple fault had occurred. And the fuses were obviously, something had happened. They were the wrong fuses. They weren't suitable. But the actual fault was that one of the infrared light curtains, a rectifier had failed in it and blown the fuse. That's the problem was. And they'd got their local dabbler to have a go, and he'd obviously opened the panel and started poking contactors in that control the motors. I'm pretty sure that was a press, so it would have basically been one big motor, and it would have had star delta on it to actually ramp it up to speed. He'd obviously poked in both contactors and basically shorted out all three phases simultaneously because they weren't mechanically interlocked. And the fuses had not protected. I don't know if he was injured or not. The people in the factory said there was just a massive explosion from the machine, and he was like thrown back from the panel. And inside, all the wiring was burnt. All the insulation was off the wiring. All the components were burnt. It was just black inside the control panel. It had been destroyed. It didn't blow the fuse in the machines. And, latterly, I just looked at it and said, that has suffered so much damage, it's going to require pretty much a rebuild. But it had also taken out, the fault had gone all the way back. The fuses in it, whatever they were, had not ruptured the current safely. The actual fuse carrier in it was welded in. And that had gone back and it had blown out all the power to the factory. Everything had just gone black with that massive explosion. And that's not a good situation to be in when something like that happens. So no tin foil and no wires over the surface of these. And other key points worth saying, if you have, fuse rating, yeah. Right. Substituting fuses, the only time you should ever substitute a different value is if you know that the fuse that was blown, if you found the fault, if you've not got a fuse the correct value, you can put in perhaps very slightly higher or lower if you know the current's in that range, but don't leave that in. Don't treat that as a permanent fix. Always make sure that the correct fuse specified by the manufacturer, and unfortunately, there's equipment that comes out the wrong specification. So in that case, if you've got a persistent problem, then you have to make an educated decision. You actually have to monitor the current in the equipment, measure it with a meter. Under all conditions, you have to make an educated decision and find the correct rating of fuse for that equipment and mark it in it clearly. It's not uncommon to find equipment that someone's replaced a fuse in the past and it's worked for a while, but then it's failed. And a common thing there is people putting the quick flow fuses in where a time delay fuse existed in the first place. And the fuse rating was correct, but the characteristic was not. So, if you've got a persistent problem with fuses blowing, you have to consider, is it an actual fault, or is it that the fuse has been changed at some point for an inappropriate value? And unfortunately, that works both ways. People can put bigger fuses in, and you just never know until a major fault occurs and damage occurs. So sometimes when you get new equipment that is second-hand, it's worth actually checking all the fuses and making sure the correct ones for the task and the correct ratings. So it's a complex sort of area, but once you get your head around it, it's quite easy selecting the correct type of fuse, and that will avoid potential problems. It just offers closer protection and also nuisance tripping. So it's an interesting subject.